In this video, we're going over the concepts for Chapter 10, which is titled Carbonyl and Carboxyl Compounds. We are first going to learn what is the difference between a carbonyl group versus a carboxyl group. A carbonyl group is characterized by a carbon atom that is double bonded to an oxygen atom. Also, that C double bond O will be bonded to two other atoms via a single bond. In a carboxyl group, we have a carbonyl functionality connected to one side to a single bond to oxygen. And if that oxygen is connected to hydrogen, that is known as a hydroxyl group. So a carboxyl group indeed is a carbonyl group, and hydroxyl group, that's where the name carboxyl comes from. First, we are going to determine and learn about two functional groups that have the carbonyl functionality in them. Those functional groups are known as aldehydes and ketones. In order to identify an aldehyde, this is going to be a molecule that has a carbonyl group, meaning a C double bond O, that is connected to hydrogen on one side of the carbonyl group. It really doesn't matter if the hydrogen is pointing towards the right, like you see here, or is pointing towards the left. As long as you have a C double bond O connected to hydrogen, and on the other side, you have a carbon chain. Because remember that R, we have learned throughout our discussions in organic chemistry that it is the rest of molecule. And in this case, for aldehydes, R is going to be basically carbon chains. When we actually write aldehydes in a condensed form, understand that the way that we write it is putting the R group that is connected to the carbonyl. And I'm going to use my highlighter tool so you are able to see it. This C double bond O connected to H, we condense it as CHO. So from now on, understand that CHO means aldehyde. When it comes to a ketone, in a ketone, we're going to have a carbon double bonded to oxygen, meaning carbonyl group. And on each side of that carbonyl, we're going to have carbon chains. You can see here in this general form, we see the carbons illustrated, but those can extend. When we write the condensed structure, specifically for a ketone, how we write it is that in a way, this area of the molecule is going to be the first R group. This area of the molecule, it can be the same or a different R group, and we just symbolize it with R prime. And lastly, what happens is that the C double bond O of the carbonyl is written as CO, and that's the condensed form for a ketone. In figure 10.1, we have the ball and stick models for functional groups that are present in these molecules. On the left, let me zoom in, we have the molecule called formaldehyde. Formaldehyde is the simplest aldehyde because it only has one carbon atom and it has hydrogen on both sides of the carbonyl. Next, we have acetone. Acetone is the simplest ketone. And it is the simplest ketone because our carbonyl group has a carbon with three hydrogens and a carbon with three hydrogens on both sides of the carbonyl. Aldehydes and ketones are used across industries for their reactivity, solubility, and versatility. I just mentioned that formaldehyde is the simplest aldehyde, and it is a compound that is widely used as disinfectant, and it is a tissue preservative. We can see in figure 10.2 where formaldehyde has been utilized to preserve biological specimens. Ketones are also used as solvents, and they are found in the formulation of coatings, just improving application of them and drying time. It is just an important solvent. You can actually find it in nail polish and nail polish remover. We can see in figure 10.5 that we have specifically a ketone called 2-methyl cyclohexanone that it is used as a solvent in varnish. When it comes to finding this functional group in biological systems, it is important to note that aldehydes and ketones can be found in biomolecules. For example, in the next chapter, in chapter 11, we are going to speak extensively about carbohydrates. Glucose, which is a major source of energy in living system, and it is an example of a carbohydrate, has specifically in its structure an aldehyde molecule. On the other hand, another molecule that is also known as a carbohydrate, fructose, which we can find it in fruits, it has a ketone in its structure. And we can see it right here. So it is important that we remember these functional groups as we continue to progress throughout the semester. Now let's learn how to name aldehydes and ketones. You can see on the left side of the slides that specifically we have the rules for naming aldehydes and ketones. Instead of reading the rules, I'm going to name all the examples that we have in the slide in order to discuss the rules for naming aldehydes and ketones. I'm going to start by naming aldehydes, and the aldehydes that we have in the example are the top two molecules on the right side of the slide. When we are naming an aldehyde, understand that similar to what we have seen in previous chapters, when we're naming organic molecules, we need to find the longest continuous chain of carbon atoms. In the case of the aldehyde, the carbonyl group is always going to be carbon 1. And when we look at the molecule on the left, we can suspect that this molecule can have a series of different long chains of continuous carbon atoms. So at first you can say that one possible long chain carbon atom could be this one, 1, 2, 3, 4. Another possibility is 1, 2, 3, 4. But then if we look at the third possibility, we can go 1, 2, 3, 4, 5. Since that is the longest carbon chain, that's going to be our parent chain. So let me highlight it for you. We are still going to use the format that we have learned previously, meaning doing a prefix followed by a root, and then we have an ending. In this, we do it when we are going from structure to writing the name. As a reminder, when it comes to this, the prefix is going to give us location and name of substituent We're going to see that specifically the root in this case is going to be the alkane name of longest carbon chain. And additionally, let me just rewrite this. We are going to omit the last E in the name because we have an ending specifically given to aldehydes. The ending that is used in aldehydes is going to be the suffix al. So for example, in that molecule that we have on the left, we're going to start with the root and ending, which establishes that since I have 5 carbon atoms, and in aldehydes, carbon number 1 is always the carbonyl. I have 1 carbon, 2 carbons, 3, 4, and 5. That means that the root name is going to be pentane, but we are going to omit the last E. What we're going to do is that word, we're going to put the correct ending. Since this is an aldehyde, we're going to put an Al. So the parent chain that is made by the root and the ending is pentanal. We can see that coming out of that parent chain or longest continuous chain of carbon atoms, we have a substituent out of carbon 2. If you go back and revise in chapter 8, specifically slide 15, you will be observing that a substituent in which we have a CH group connected to a CH3 and a CH3, that is called isopropyl. So the prefix in this molecule is going to be 2-isopropyl. And then the root and ending is pentanal. Aldehydes can be aromatic. And when we have an aromatic aldehyde, we have to treat them different from a straight chain aldehyde. In aromatic aldehydes, the benzene ring and the CHO group, because remember that we learned that CHO represents the CHO in the aldehyde. That whole motif is going to be always our parent chain when we have an aromatic aldehyde. That is actually called benzaldehyde. Whenever we have an aromatic aldehyde, different from the straight chain, carbon number 1 is not going to be in the carbonyl. Whenever you have an aromatic aldehyde, the carbon atom that is holding the CHO group, meaning this one, is going to be carbon number 1. Then, based on the substituents that you have in the molecule, you may have to go clockwise or counterclockwise in order to give them the lowest number. In this molecule specifically, we have to go counterclockwise. This is carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6 to actually determine that carbon 3, since it has 1 carbon, 2 carbons, that is an ethyl group. So for this molecule, this is a 3-ethyl benzaldehyde. So let me actually move the benzaldehyde closer to the 3-ethyl in order to write the correct name.